All right, so we are up for the day's statistics torture session. So, all right, so I think almost everything we're going to talk about you've seen before, and so now you'll just see it again, and hopefully, my guess this one will be fairly conceptual, a few formulas here and there, and then we'll cover some of this stuff in the lab for those that can handle that. Also a reminder that for anyone that wanted to, at lunchtime, I think Chris and I will be around the lab to just help you with learning basic R stuff. So if anyone wants to do that, feel free to drop in. And then what am I going to talk about? So I'll talk a little bit about Markov Chain Monte Carlo, very basic, and then also Gaussian processes, very basic. So the climate people got to talk about problems, and here's how stuff fits in, and a lot of that stuff's pretty far down the road statistically, and what I'll show is just sort of a starting point of here's kind of a place to start and kind of move towards these Gaussian processes embedded in these larger models that you might do for inference with a large-scale climate model. So we'll take a couple steps along that path just so you can see how that goes. My hope my hope is always that it's understandable. Maybe, maybe not, we'll see. But please go ahead and ask questions any old time. Even if we don't have the microphone, it'll be okay. I can repeat them or something for the video, which will be watched all the time, I'm sure. All right, so what do we have here? We've got, so this is the picture of the inference with a emulator response surface, and so here's the idea. So in that top left corner, oh yeah, thanks. Top left corner, we've got the result of, we got the result of a number of model runs, about 20 of them here. And so the model output, I'll use eta because we like to change notation with each speaker all the time for everything. So now we have a new notation. But eta is the model output. Maybe it's 2-meter air temperature, something like that. And usually the output is indexed by a couple of things. For the model, there might be a model parameter. And so t or theta I'll use as a model parameter. So it's something that is a parameter that's inside your model. You don't know what it is, but you can run the model at different instances of that parameter setting. Also, there might be other inputs which aren't parameters, but maybe index, say, space or time, or they might index initial conditions in some sort of way. So I usually use something like x for that. So initial conditions or spatial location, and then the model parameter. So at a different input setting, you run the model and you see what the surface temperature is. So the height of those green dots, that tells you what the output is from the model. And so if I took that picture and kind of just tilted it a little bit, it's exactly the same green dots here. And now for the parameter, I've moved it between 0 and 1. And so this parameter here now goes between 0 and 1. And at 0, I get the high value of the model, and as I move theta down to 1, so maybe it has something to do with clouds or aerosols, I get a low value for the model. But I can't run the model at every single value of theta, so I can only run it at certain settings. So the green dots are where I actually run the model. And then we might have physical observations, and so that's what the black dots are. So these are observations of the actual system. And so those are the black dots, and often you have uncertainties, but if you listen to Charles, right, maybe you don't really have uncertainties attached to them. So if you did, the black error bars are representing uncertainty in your observations. And so you may not know the observations exactly. You can't see the dependence here, but you might say they're dependent, or you might not say that. But basically, the observations are going to have some uncertainty attached to them, and you may or may not know it. And so one strategy for dealing with this problem is to say, well, all right, the computational model is very demanding, so I can't run that a whole bunch of times. So what I could do is run the computational model at a number of input settings. So here's 20 runs at 20 different settings of x and t, or theta. And then I can fit a response surface to this output. So certain outputs are very amenable to this. Other outputs, maybe not so much. But what we'll learn today is a little bit about how to fit this Gaussian process to this sort of data. And so what you see here is the posterior mean of a Gaussian process right here. So it predicts what the model would have said at places you didn't run it. And so this is very handy because now you can do all sorts of searches or parameter searches around this surface and figure out what settings in the parameters seem to be consistent with the observations that you have. All right, so the idea of using an emulator for a computational model is exactly captured right there. All right, and then I'll make it way worse with equations and stuff later. So if you got that one picture, that's it. So here are different variants of this, because in the last 10 years of my life, I've done nothing but make these pictures. And so I better show them, right, if I've spent all that effort on them. So same basic picture, right? Model runs, physical observations, parameters, response surface, Gaussian process. In a nice setting, we might say, oh, here's the estimated or the model parameter estimated from the data, or the calibrated model parameter, sometimes we call that. We might also put in another term and say, oh, between what the model says and where your observations are, there might be this systematic model discrepancy. Charles mentioned that. So in this example, there's a single parameter setting that seems to be very consistent with the observations that you've got. And so if you went and did a big statistical model, you probably wouldn't estimate much model discrepancy here. And usually you put a prior on the model discrepancy that says, well, try to be 0. And then if you can't do that, here's how you can deviate from the model. You might have to deviate in a way that's smooth over space. You might want to deviate that changes this output, but not that output. So you might have a lot of structure in how you think it might deviate from reality here. But this one is sort of the nice situation, right? That the model and the physical observations seem to be in line here, and there's no reason to add a discrepancy, and then you can make predictions for the system at new settings. And so that's just sort of this last plot here. And then what happens often is something more like this. In fact, almost always this happens, that if you have enough outputs that you look at, so for any given parameter setting, that's one of these green lines. There's no green line that goes through all of these data points. A green line will match this one, but miss these guys over there. It'll go through these ones and not hit that one. There's no way you can match everything. And so in that case, you have to do something in your statistical model to say, how is the data related to the model? Usually we say the data, what we'd like to say in statistics is that the data and the model are related. If you just find the right parameter value, the right value of theta, then the model and the data will agree up to some small epsilon amount. And now we have to add something else in here. So we have to add some other stochastic term to say, how do we get agreement between model and observation? And so this one uses a Gaussian process for the discrepancy. So it's saying you have to have some smoothness across this dimension x, which might be space. So we say, OK, we're going to enforce some smoothness now. And now when it fits this whole stuff together, here's what it comes up for the model discrepancy. It dips down a little for this observation, then it comes back up for this one, and kind of interpolates in between. So now you have predictions for the actual true physical system you're looking at, which don't really match what the model would say. And the other thing that happens here is if you have any sort of amount of discrepancy between your model and reality, you have a hard time hunting down your parameters. And so remember before, the model parameter distribution was really tight around the right value. Now, because there's a lot of uncertainty, the discrepancy, you can wiggle this around and you change the parameter settings, that those two things trade off a lot. So there's a lot of ways you can change the discrepancy and change your parameter setting and still match the data. So this basically means that if you have to entertain discrepancy, it's going to be very hard for you to figure out what parameter settings are really consistent with the model or with the data. So discrepancy makes life hard. And then what's the other basic rule? Almost every single real application is going to have discrepancy in it. So thinking about how you want to model that is an important feature. And Charles was mentioning, well, maybe which data do you pick? If you thought about that, that's actually one way of picking a discrepancy model. That if you had lots of outputs and say, oh, I'm only going to try to match temperature and I'm going to throw out everything else. Well, basically, you're having a lot of discrepancy on everything else and saying, I want it small for temperature. So these ideas aren't new or different. It's just encoded in a special way here. All right, so that's the basic idea. These are the concepts. And what we're going to do is maybe go through a few from the ground up statistical ideas that kind of get us there.
Question.
Yeah.
So, on this issue of the discrepancy, does it depend at all on the complexity of the model that you're trying to fit? The higher you get, the more discrepancy terms you need?
Yeah, so Does it depend on the complexity of the model? Usually if your model is very complex, then your system is very complex, right? And it might be a very hard thing to model. So in the sense that if that's your model, I'll bet your system's tough to model and I bet you're going to need it. But in principle, you don't necessarily need it. It's not, arguably, the more complex your model is, maybe the more ways it can fit the data and within the sort of the parameter settings that you've got, and you may not need that. A good example might be, we'll talk hydrology, but if you make your hydrologic model just you're estimating permeabilities over some region, and the very standard way is say, oh, let's make it into geological regions, and then we'll have a single permeability for those 7 regions you got. You could kind of pixelate the thing or make it continuous and just say, okay, now I'm just going to have permeability that varies very smoothly across this thing. That has so many parameters. I bet there are configurations of permeability that match your data so that when you pump water through and look at contaminant transport times, you'll get that thing right. So that's a very, very highly parameterized model. Depending on how the permeability field is, it might be very complex looking, following Darcy's law. But that's a setting that has a very highly parameterized model that probably you're not going to need a discrepancy for if you do that. Whereas in other settings, you'll have a much more constrained set of parameters, a handful of them, and probably you will for something like that. So it varies, I think, in that one. So as all my answers will be, except when we get to maybe formulas, there might be a right and wrong answer, but most of these things will be, yeah, it depends. All right. All right, so now super basic statistical kind of idea here. I'll talk to this side of the, because that way I won't be in the, now I feel compelled to move. All right, so here's a statistical model. So the statistical model is my data follow this uniform distribution. So this is a density for a uniform, meaning anywhere in between any point within this interval is equally likely. And the uniform distribution is centered at this black dot. So that's my model for the data. And now what I'm going to get as realizations are these circles here and there. So they're going to show up randomly across this distribution. And so the question might be, well, what I'm really going to do, I'm not going to know what the actual center of this distribution is. I'm just going to know, like, OK, I've got a uniform model for my data errors. And what I'd like to do is estimate where is the black dot given these white circles. Right? Statistical problem, we'll have a likelihood that shows up. And then this is just gratuitous figures down here. It doesn't really mean anything, except we have physical observations and models. So in a way, that's what we've got here. We've got a model for the error distribution, uniform. We just don't know where it's centered. We don't know where that black dot is. But we do see the realizations circles there. All right, so that's the setup. I pick uniform because it's good for reasoning about stuff. So what does that mean? That means I have 4 realizations, right? So here are the 4 dots. I've just put them on different lines here. So this is our data, these 4 dots. The question is, where is that black dot, right? Where is the center of the distribution? So now if I just ignore everything but just think about this one circle here, where is the black dot? It could really be anywhere at a distance plus h or whatever this is, or a distance away as far as the uniform goes in either direction. So the black dot could be anywhere along that sort of uniform where it goes up from 0. All right, so in a sense, that's a likelihood function. That's saying where is it where might I see the black dot? And the black dot's usually a parameter, right? The center of the distribution. So no chance is it here. The chance of 1 over the height, 1 over h, all the way across here, and then it goes back down to 0. So the likelihood is non-zero around here, and then it's 0 over there, but it's flat in between for this model. For other models, that would be different. All right, so there's the likelihood. It's telling us something about the black dot. Same thing for each of these, that all of these are making their own statement about where is the black dot. Uniform's also nice because it tells us dependence and things are a lot easier with that. All right, so now at the end of it, we see these 4 black dots. What can I say about the black dot now? Where might it be? Oh, I'm so mean to make the audience participate, right? All right, so all right, I'll move my finger and say, can the black dot be here? All right, so all of them say no to that, right? What if I move up over here? All right, this guy says it's possible, right? But 3 others say there's no way. Where can we go? Can it be here? No, not yet. All right, where? Yeah. All right, so that is as low as it can be, right? Because they all have to agree that the black dot might be there. So the lower bound is here, and then you can go up here. Like, yeah, there we go. If you go any further, someone's going to say no. This guy's going to say no, you can't go any further. So we really have a much smaller range about where the black dot could be. All right, so that's these different components of the likelihood are all chiming in to say, where is the black dot, right? All right, so that's what likelihood is doing. And so there's the answer. There's all your data. And the question is, where is the black dot, or where is the parameter? Where is the mean, mu, things like that? That's telling you where it is. OK, so this is independent data all chiming in to say, there's where the black dot is. What else can we do? All right, let's change the model a little bit. So a more common model, and usually a much better model to have, is something that doesn't have these real rigid, all of a sudden from something to nothing tails attached to them. So here's one that has gentler tails, normal distribution. But we have the same problem here. So now we want to know, the black dot is the center of this normal distribution. We observe these same white circles, right? And now we're going to just see the circles and ask, where might the black dot be? All right, so we'll have the same picture. And uniform one's nice, right? Because you can just, by pure thinking about it, without knowing any statistics, say, oh, there's where the black dot ought to be. It's somewhere in between that range. How does it work for the normal distribution? All right, so this is what we learn in statistics. And they'll tell me that in the cult of statistics, we shouldn't share this with anyone, but I'm going to just this one time. So how do you figure this thing out? If you thought about, oh, what did we do here? We found like the common places, but we found the region that was the intersection of them all. So that's really just the product of all these things, point-wise. Same thing there. So if I just take the product of all these things and I have a normal distribution, there's a theorem that says, oh, the product of normals point-wise is going to be another normal. So here's what I say about the black dot. So it's telling me the black dot is likely between here and here, but there's no hard upper or lower bound anymore. It could be minus infinity, it could be plus infinity, just with very small probability according to this model. All right, so this is just independence kicking in as you go down this thing. So independence means we just product up these likelihoods, and then we end up with a statement about where the black dot is. OK, so when we make likelihoods, we're usually doing something like that. And I'll get a little more detail on this in a second. But also things like the central limit theorem. This is the central limit theorem happening here. So this thing gets smaller by a factor of 1 over root n, the number of observations you got. All right, tricky question. For the uniform case, does this thing shrink by 1 over root n? So the answer is it shrinks faster than that. It shrinks by 1 over n. And so it's because it has these real hard tails. This isn't important, except that you shouldn't really use the uniform because it has such hard tails that it usually gives you unrealistically tight inferences. So only if you really knew the thing was uniform might you try this. That almost never happens. There was this problem I remember in graduate school where from World War II, the Germans would number their tanks as they came off the assembly line. And so a plane would fly around and you'd spot numbers on tanks. And then you had to try to estimate how many tanks were there. So uniforms came in for that. That's the only one time I noticed that. All right, so basic concept there. Now we'll go back and we'll do this with formulas because that makes it so much better. Oh, yeah. You betcha.
How do you, estimate the h? You assume?
Yeah, so I didn't estimate the h in this case, did I? Yeah.
You just assume that there is an h.
So I did for this example, and in real life, what you can do is you can also make the h uncertain, and so now instead of just these choices, right now you have a bunch of choices. You can have h-axis go this way, and you have skinny ones and fat ones and things like that. And what you would like is h's that make the likelihood high in the end. So at the end, so suppose we had one h here, and now over here we could have a slightly wider h, and over here we'd have an even wider h. H's that are too narrow won't have any likelihood at all here. And h's that are really wide, the result is going to be something wider here and shorter. And what you want is things that give you a high likelihood. So it's going to pick the H for which you get the highest height here. So, so yeah, there are principles to get at that. And it just doesn't follow as well in pictures and things like that. But yes, so if you're trying to estimate the H as well, same basic thing, but now you're going to search over different regions of where the black dot is, but you're also going to search over different widths. Yes, that's a good question. And we'll do some of that maybe. Maybe at the end of this thing. 12:30, right? I'll make sure we're done by then too. Okay, so now I'll do the same thing and I'll add just a few other equations in here just so we can see it mathematically. And then mathematically it'll work well for throwing the H in just as well. So same basic picture here, right? We got a model parameter and we've got some space over which we get the observations. So X might be initial conditions, it might be space, something like that. Theta, the parameter. I use zeta for, I never really use it here, but it's the true physical system. So it's nice to separate things. We've got the actual physical system and we've got our model, right? So they're two separate things, and mostly we'll talk about the model, but reality, or what we observe, is always going to be the physical system, maybe plus some observation error. But we're always going to model it as what the computational model might say at the right parameter setting plus some error, and that error might also include discrepancy. Okay, so computational model eta, I'll usually have two indices for it, x and theta. Observations, I'll use y, and then just observation error, epsilon. So we're not going to touch discrepancy, I think, for most of this time. But just remember, you can throw it into E there if you wanted to. All right, so there's the basic setting. And now we can even pick 5 data points, right? So if you're really excited about this in the lab, we can take this data set and put it out here. So here's the data set, right? And we've got x values, we've got y values. And so we can just go ahead and let's not worry about the model being hard to evaluate. Let's say we can easily evaluate it at any theta for any x, so that instantly we can figure out this whole green line. So we put in a parameter, say 0 for theta, and we get this top green line. As we move it down, our green line just kind of moves down as theta goes from 0 all the way down to 1. So there's the model going from theta equals 0 to theta equals 1. So the question is, how do we get to that blue part if we do it with math? And so here's the likelihood chiming in, right? So the likelihood is really just this product of normals, one for each. So we have this independent normal errors. And so if we go ahead and look at that, what we can do is let's pretend we have the red data set at first. So here's where our observations are. We have errors whose precision or variance is 1 over lambda, or 0.25 in this case. So what we can do is just move theta from 0 to 1 and just look at what the likelihood is. And so it's just going to be this normal product of normals for each of these guys. And so if we just go across, it'll get large and come back down again. So the red line is giving us the likelihood if the data were the red dots. All right, so that's just according to this normal formula here. So it's just e to the minus 1/2 something quadratic. Assume we know lambda y for now, so let's not worry about the width on that thing. Likewise, if we had, all right, so the red dots favor a value of theta that's somewhere around 0.4. If we had the black dots, right now we just go through again, we just move theta from 0 down to 1, and it's going to favor a value of theta that's about 0.6. All right, so that's just likelihood. That's just computing that as if it were a function. Also, the likelihood looks a lot like a density. It's not quite a density, but it's almost that. So it's useful to think of it that way. All right, so what we're going to do is combine the likelihood, that function here, with a prior to end up with a posterior distribution to give us inference about the unknown parameter theta. And so how do we do that? Bayes' rule again, but of course in pictures this time. So we've got a uniform prior for theta, anything between 0 and 1, uniform. We've got the likelihood that you saw. I guess we use the black dots, right, because it's centered around 0.6. If we take the pointwise product of these two things, now we get a posterior. So when I showed you the likelihood where we just multiplied these independent things together, it's not guaranteed to be a density, meaning it's not guaranteed to integrate to 1. However, if you multiply it with a prior, well, it's guaranteed to have a finite integral, and now you just might have to renormalize it. So what I didn't show you here is renormalizing this thing. But now this guy is basically telling us our inference about theta. It's somewhere inside this distribution, and more likely towards the middle where the likelihood's high or the density's high, and less likely towards the edge. But certainly not very likely at all to be outside this place where you've got mass. All right, so there's Bayes' rule. Everything just works from that, right? So it's just this pointwise product of the prior and the likelihood. And most of what we do is just figure out, well, how can we, all right, we mathematically have this thing. How can we generate realizations from this thing so we can see what kind of values of theta are plausible? So in 1D, it's not such a hard problem. If we're in 1,000 dimensions, then it's a pretty hard problem. But the same principles will work in either case. So we'll tackle this 1D problem, but it'll certainly work in higher dimensions. And so if you go back to think about that H problem, so that's the width of this thing, that could also be a term in your likelihood, right? And that could be an extra unknown parameter. So now instead of a one-dimensional thing, it'd be a two-dimensional thing. And the same thing will work here. You'd have a two-dimensional posterior for theta and H, the width. All right, so Bayes' rule. This is only like, how many times have you seen that now? And every time it's different? Yeah, okay, so now we'll look at it again. Here's Bayes' rule again. So the prior on top in green, and now I've broken up the likelihood into the independent components. And this is because in our model, we've got independent observations or errors on the observations. If that wasn't true, then this picture would make less sense. But there we have the contribution of data point 1, 2, 3, 4, and 5 all coming down there. And in the end, we've got the product of the prior and all the different likelihood pieces, and we get this guy, right? And all the likelihood theory where you get convergence and things like that for to a normal distribution, that's what's happening here. So it turns out that if you have independence and almost any distribution for these guys, in which the distributions aren't getting super skinny or not getting super fat, you'll get this property if you have independence, that you'll end up with a normal here. So if you have a fair bit of independence in your data, it's not going to be real crucial to get this model exactly right. It's crucial to get its width about right, but you're still going to get this very normal looking posterior. So that's one thing that saves us from some of our sins, is that lots of data will save us from things, and things will look normal regardless of not getting the model exactly right. So if we use some other model instead of normal that came around with exponential tails and a point at the top, same thing would happen here. Of course, if we used uniform for our likelihood, that wouldn't happen here. We'd get a uniform looking posterior. So all bets are off because the tails behave differently, and then asymptotics and everything behave differently there. All right, so that's what we're doing. So we end up with that posterior distribution, very normal looking. And what we want to do is have a general recipe for sampling from that thing. One dimension is kind of easy. 2 dimensions is easy. Like, we get up to 5, it gets hard. So it very quickly becomes hard to sample from something like that. And in general, what we have here is not exactly the density. We have the density with some unknown normalizing constant in front. So we've got the density, but we don't really know exactly how to normalize it. But we do know that it integrates to something finite. So there's what we got. We can evaluate it. We can put in values of theta and evaluate what the outcome is. So that's basically what we have, and that's what sort of motivates this Markov chain Monte Carlo ideas. So Markov chain Monte Carlo, and Gabriel gave you an example of that. Usually works something like this picture here. So here's this posterior density. So now we have something two-dimensional. What you do is start at any old place, and we'll try this in the lab. And typically, what's commonly done is you update one component at a time. So it's going to update, sort of this x2 component, then the x1 component, then the x2 component, then the x1 component. So it's just going to keep cycling through. And if you do it with the right rules, you can be assured that this track that you get, and if I look at it marginally, look at where all the points are, it follows this density. It follows the posterior density. So that's what you're doing with Markov chain Monte Carlo. You're sampling from this posterior. And what's nice is that all you need to do is just evaluate the density up to a constant. So all that's really required for that is just to do that. And so as long as you can do that, you can do something like this.
What do you mean by doing it with the right rules?
Yeah, all right, I'll give you some rules. So here's the most common rule, and the right rule means it's a rule that provably says that the limiting distribution, or this chain, converges in distribution to the posterior distribution that you have, and so this will be an example of doing it one way. So start at the blue dot. So here's the rules in English and math, both of those languages. Oh, but I won't use either of those. All right, so we start with the blue dot. So now what we want to do is sample from this posterior density. So this is exactly the posterior density we had from that problem. We start with the blue dot, and now what we're going to do is we're going to generate a new realization that's uniform, centered at the blue dot, but can be anywhere along that red line. So uniform on that red line. So I generate this red guy. And now what I do is I either accept or reject this red guy according to the Metropolis rule. And the Metropolis rule basically says compute the acceptance probability, which is just the ratio of the density of this new guy, red, over the density of the old guy, blue. So because we don't really need the normalizing constant because we have the ratio, they'll cancel out. And so basically it's always going to move to that new place if the density of this red one is higher than the blue one. So it's always going to move there. If the density of red is not as big as the density of blue, it might move there, it might not. And it moves there with this probability, the relative ratio of the densities. So if you do that for your rule, you're guaranteed to, in the limit, get a Markov chain whose distribution marginally looks like that density there. And why is that? So you can see why, because take any 2 points and ask, what's the chance of moving from this point to that point? And what's the chance of moving from this point to that point? And they are exactly what you would get if the exact chances of moving are proportional to the heights of their densities. So this is why that works. So it's called a detailed balance. So it's a pretty strict condition, just saying anytime I move from this point to this point, I have to do it in the right proportion of time. So it works pairwise, hence it'll work across the whole density. So you just have to make sure your Markov chain will explore everything. So that's what's going on here. Propose this red guy. Look at the acceptance probability. This one actually has a higher density because you can kind of see it over there. It has a higher density. It's going to accept. So now we're at the blue dot. Blue dot, we propose the red one. The red has a much lower density than the blue dot for this case. We randomly accept it or not, and this one happened to reject. So now we stay at the blue dot. So we started red, and now we stay with the exact same value. And now we're going to do that. So now we move to the next step here, and now we do it again. Here's the new value. It's probably a pretty comparable density. It turns out to be accepted, and we move on. So if I just collect the blue dots that I've got going around here, notice some of them repeat, right? But I'm following this Metropolis rule, which means pairwise everything is going to visit each other at the right amount of time. I'm going to get something that follows that density that I have. And in fact, this is the workhorse of most of the Markov chain Monte Carlo. It's something like this. So what's wild is you accept or reject regardless of what I use for my density here. So as long as I use something symmetric, this is true. If I don't use a symmetric density, if I use a density that's more likely to be a lower value than a higher value given where I am, I have to change these rules a little bit. But the way you change them is so that if I look pairwise between 2 points, I have to visit the 2 points at the right rate that corresponds to that density. All right, so that is Markov chain Monte Carlo. We'll play a little bit in the lab for that. It also works, I showed it in a univariate setting, but it also works in very high dimensional sorts of things too, that you can imagine starting at a point. Let's go 2 dimensions here. As long as I do a proposal that's symmetric around that, I could accept it or reject it according to that density, and I'd move along in that way as well. Ben?
It's really fair to say that the Markov chain is a good way to converge on the most likely, it's a calibration tool rather than a way to explore the tails. Can you also use this tool?
Yeah, so this will give you, all right, so this will give you realizations from that density. So you'll see things in the tail at the proportion of probability that's in the tail. So it's not great if you really want to ask what are the wild events that could happen, because it's only going to explore a 1 in 1,000 event 1 time in 1,000 about. So there's tricks you can do to try to push things out there if you'd like that. But yes, it's not really going to find a mode. In fact, it's not going to be very good at finding a mode because it's always doing these kind of big steps. Yeah. And also, if you thought about it, we'll see this in the lab. But suppose instead I didn't use a uniform that's, of course, corresponds to this red line, but I used one that's 10 times as wide. So it goes from the ceiling to about here, so it's still symmetric. If I use that for my proposal, what's going to happen most of the time? Yeah, it'll reject because if you have a real wide proposal, you'll probably propose something, you know, on the screen, but the density of that point is going to be almost 0. So it's always going to stay where it was. So if you have a really wide proposal density, yeah, in the limit it's fine, it's going to work mathematically, but you're going to stick a lot. So it's not going to be very efficient. Likewise, suppose I make the proposal width real small, about the width of the dot. What's going to happen? Will I accept a lot? I'll do lots of accepting. Will I move very fast, though? No. It'll be like me in like 20 years from now, right? So yeah, eventually I'll get some rejections and I'll move the other way and stuff like that, but it's going to be a lot of steps in between. So that's also not going to be efficient. So it turns out that you want your width to be about such that you reject about half the time. That's a good sort of rule of thumb. And yeah, good question. When do you stop? All right, so what you want, your goal is to explore this thing. And so when you feel like you have enough, you've explored this thing pretty well, and you feel like you've covered things, you're not just stuck on one side or the other, you can stop. Now you can do more sorts of tests. You can ask, do I feel like this chain, even though it's dependent, do I think it's covered everything? And you can look at autocorrelation and sorts of things like that to ask, is it enough? A good rule. It's hard to be just looking at it and ask, did it explore the whole distribution? So often what might happen is you'll see the trace and it'll be up here for a while and then it'll be down here for a while. Or we saw some of Gabrielle's traces yesterday. Well, it kind of went up and down. It didn't go that far. I'd like to see up and down a lot of times. That gives me a sense of if it's traveled back and forth a lot, it's probably sampled the whole distribution. So a lot of that, you can do that visually. You can do more formal autocorrelation checks. But that's something you want to do because you want to make sure you have sampled that whole distribution. And especially if you care about things in the tails.
So thinking of like the ice core problem, where you're trying to estimate the Del-O-18 or temperature for the particular ice core level, but you actually have layers where you know that one is before the other. You don't actually know the timing either.
Yeah.
You're trying to fit both the time of the event
Yeah.
and the amplitude of the event in the time series setting.
Yeah.
You know because the one layer is above the one before it, and the one after that is below it, that there's some restrictions.
Yeah.
Your proposal density would have to be. So
Right. Yeah.
possible? Is that
Yeah, yes, and I think, so in some ways it's kind of like it's a pair of 1D image problems with this constraint that you'd like to have this isotonicness or monotonicity in the times and also maybe in the other measurements, the widths or the core. So yes, I think that's very doable. And I would like to couch it to say, okay, now I have a prior distribution for the times. I have a prior distribution for the measurement that goes with it, and put constraints on that prior saying, all right, first one has to be before the second one, which has to be before the third one. And so then when I make proposals, I have to reject something that violates that constraint. And that should flow pretty well with something like that. Famous last words, right?
Sorry, do you mind if I'm slightly confused with the point you made about the wide
Yeah.
or the narrow distribution?
Yeah.
Because the probability is a ratio.
Right.
Do you mind just...
So let's just walk through this. So let's make it wide, right?
Yeah, so I can understand that the probability then is very small in a location, but you've got a ratio between theta t and theta star. So
Right. So I'll generate a theta star, which would be a red dot in my language in the picture, right? So I generate a blue dot. I'm currently at a red one that's somewhere kind of in the middle here, and then I generate a blue one that's maybe here.
right.
So now the density of the blue one, theta star, is 0 about, And the density of my previous one, well, it has to be somewhere around here. So it's going to be something, but positive. Oh, you can see my album collection now. All right, so without that distraction there, so something 0 over something positive now is going to give you an acceptance probability of about 0, meaning it's not going to accept that thing. It's going to stay where it was. Does that make sense?
Yeah, somehow I kind of imagine it normalized in my mind. But
Yeah.
because you've got a wider. Okay, I'll think about it. We've discussed it.
Yeah. So if it's real wide, you'll probably generate a blue dot that's going to give you an acceptance probability of about 0, meaning you're going to stay where you were. So what will happen is, imagine this thing being real wide, right? We'll be at blue. Sorry, I keep changing the colors on you. Sorry. We start at blue, we generate a red, but it's way out there. You're going to reject it and stay here again. So you'll keep doing that. So you'll keep staying where you are because your theta star is so unlikely relative to your current value. So maybe I wasn't clear on this point, though, that you make a proposal, you make this proposal and either accept it or reject it, and you're done. You move on to the next step. So if you reject, you stay at your old value. So you have repeats quite often. And that's okay. That just means it's not that efficient a sampler. But it means you're staying at the same value a lot of times, and then eventually you'll accept something and it'll move and stay there.
Maybe the confusion is because he has in mind a wide normal distribution, but what you're meaning is maybe a fat tail distribution.
Yeah. So the density, or the target we're going for is this guy. So it's not going to like anything that's proposed way out here, right? In fact, you shouldn't ever accept something that's impossible relative to this density. But if your red line is way larger than this thing, that's going to happen some.
The other confusion may be that he's mentioning, he's thinking of the prior. You're just talking about his step size.
Yeah.
Because you're looking at the full range, right? Between theta. Theta could have been anywhere between 0 and 1, right? And as maybe a prior.
Yeah.
But that's different than necessarily the full step size.
Right.
What's the difference?
So the prior is already kind of living in this thing, that this is the posterior distribution. It's the product of the prior and the likelihood. This width of this thing is just a mechanism to sample from this thing. It's just a mechanism in the Metropolis algorithm. So it could be anything. The rule is it has to be symmetric about your current value. So it has to be symmetric about that blue dot. But it could be real tight. It could be real wide. And all of those mathematically or probabilistically are going to work. It's just some width might be better than another width. It's good. Like, all right, this is. We can talk later, though, for sure. But the point is, really, it's just a mechanism to sample from that density. But understanding that stuff will give you some intuition about it, so it'll be good to try to digest that one day. And look at the albums that I have. All right, so there it is. All right, so there it was for just 3 steps. And notice it's stuck at the same value a number of times and then would move around. In fact, it should stick about half the time to be efficient here. And so there's the chain working for a long time. And so sure enough, if I take a histogram of that chain, it'll look a lot like that posterior density that I've got. And so that's how we get that posterior density in this little picture I was showing you. So this is really just an artist's rendition of what that is. All right. MCMC, now you're all experts. Sorry, almost all of us. Anything else to say here? Not really, except that we can do this in 2 dimensions or higher dimensions. What's hard? All right, so what happens in 1 dimension? We notice that if our proposal width was real wide, we reject a lot. So we want the proposal width to be about the width of the density. So you want to get that about right, just because it'll be more efficient, not because it won't work. In higher dimensions, the same idea works, that you can propose something in high dimensions that's symmetric about the current value. But to get something right in lots of dimensions at once, so you could do, say, a normal proposal that's centered at the current value, you could do that, but you have to get a lot of things right for that to be acceptable. And so it turns out that an often easier thing to do is just to update one component at a time. So here is this bivariate normal density. Here was this metropolis algorithm kind of working one dimension at a time. So what's going on here is you're updating the first component, accept or reject it, and then you change and just update the second component, leaving the first component where it is, accept or reject it, move on. So you're always kind of changing one dimension at a time. And that's just because it's easier to find a proposal that's good in one dimension than it is in lots of dimensions. So other people have worked hard to find higher dimensional proposals that work well. And then Gabriel talked a little bit about an alternative to that. If you're lucky, you can find an alternative where you can recognize the conditional distributions. So if I just look at the conditional distribution of one component, I named them Z, right, because we want to change notation each slide. This is why I like to say with pictures. So over the years when notation changes, the pictures really do stay the same. So if I look at just one component, say Z1 dimension, given a value of Z2, if I look at this cross-section, often I can recognize that distribution. So in this case, it'll be normal. If I have a bivariate normal, all cross-sections or conditional distributions are also going to be normal. So sometimes I can, instead of replacing Z1 with a metropolis draw, I can just replace Z1 with a draw from its conditional distribution given Z2. So that's what's going on here. So here I have a sampler that's like metropolis, but it's sampling from the conditional distributions. So sometimes you can recognize those. If you use these big computational models like we have in climate, it never happens. So sometimes in a regression model like Gabriel showed, you can do this sort of thing. But it's so rare that I'm not even going to bother covering it in this. But what's nice about that, if you can do it, it's automatically tuned. You're always going to accept every time you do that if you can sample from the conditional distributions. So that's nice. You don't have to worry about sticking too much or too little at certain places. All right, but both of those will give you a collection of points that are draws from that density. And that's always what we're after. All right, that was Markov Chain Monte Carlo. Piece of cake, right? All right, so in the lab, we'll do one MCMC kind of lesson, and then we'll also do Gaussian processes. And again, it will be a, right, we aren't going to get all the way to full climate model discrepancies, emulator calibration and all that, but you'll at least get some of the basic ideas. All right, so this all depends on the multivariate normal model, so I'll spend a little bit of time on the multivariate Gaussian. So what I've got here, and I'll stay over here on this side so Charles doesn't have to change the camera again. What I have is a vector of 1, 2, 3, 4, 5, 6, 7, 8 points. So I have 8 points that kind of live in this space going across, right where the circles are. And if you have good imaginations, you can imagine maybe 1,000 points living across this space, right? That's what that line is. It's a lot of points going across. So you can think 1,000 or you can think just 8. Either way will work. So if I take that 8 vector and say, OK, this 8 vector, I'm calling it here Z. Oh, in Italy, do we say Z or Z here? I'm going to have to say Z because there's no way I can say Z all the time. So here we have a vector Z, 8 vector. I'm going to say it has a normal distribution, and then it has a covariance. And the covariance is a special part here. I'm going to say the covariance between any 2 points, or the correlation between any 2 points, just depends on the distance between them. So the correlation is going to be very close to 1 when the 2 points are close. And then as points get farther and farther away, the correlation is going to die off. So special correlation matrix here, or correlation function. If I use that, it turns out e to the minus distance squared, I'll get something that looks like this. So if I make a draw from this normal distribution, I'll get a realization that looks like those dots here. So what's nice is tight correlation for close points, looser correlation for points that are far away. I'll usually just go with this e to the minus distance squared sort of correlation function. There's lots of other alternatives out there, and they give you different natures of things. And so now I can actually evaluate the density of Z. It's just this multivariate normal density that we've seen before. All right. that was really all you need to know for the Gaussian process. So if you just know normal rules, everything else is going to fall out from that. All right, so here are some realizations that you could do. If you just draw, like R will have a multivariate normal realization routine that you can just draw multivariate realizations. So if I draw the 8-dimensional one, I'll get the circles there. So there are just draws from that density, where the covariance is just given by e to the minus distance squared between any pair of points. And if I did it for 1,000 points, well, there's that continuous line going through there. So it turns out these things are nice and well defined on the continuum, but practically you really only compute on some grid or something like that. So there are realizations of the thing. And so if I look at any one point, I can say, oh, okay, here's a realization. But if I look at one point, it has a distribution that, in this case, is normal, mean 0, variance 1. So if I look across this thing, yeah, the variance is 1. On average, I'll see zeros. And if this thing went for a long time out here, right, kept going all the way over to there, I'd be able to say things like ergodic properties about it. That if I took the average of that thing from 0 all the way over to a few thousand in the space dimension, there'd be enough variation in this thing that the mean of that process, if the mean of the whole thing would be 0, the variance I'd computed would be 1. And it's just that points are dependent in between. All right, so these are good prior models for functions. So if we don't know how a function is going to behave, but it's going to be a function, so we're going to imagine a Gaussian process is really a function of some variable here. This is a nice way to represent a function with all the probability you want to throw in there too. All right, so generating a multivariate normal. I'll go through this real fast. It's not real crucial, right? Programs will do this, but it's worth maybe knowing a little bit about it. So the way you generate a multivariate normal is you generate a whole bunch of independent normal 0-1s. So any program, any package will have a way to do that. And then you use this fact that if you want a multivariate normal, just take standard normals and hit them with a matrix K, and what you're going to get is a normal that has K times its mu, or K mu and K sigma K transpose is how it's going to modify the covariance. So if you hit normals with a matrix K, it modifies the mean and variance, but it stays normal. That makes sense, right? Because if you do anything linear to a normal distribution, it stays normal. So for Gaussian processes, we always want something that's normal 0 with some covariance matrix sigma. And so what we do is we just compute the square root of the sigma matrix. We generate a bunch of IID normal 0-1s, and then we hit those with the square root matrix. So Koleski will do this. SVD will do this. Koleski with pivoting will do that. But that's how you do it computationally. It's usually worth thinking about for spatial sorts of things that if you just did Koleski and you had your points ordered in spatial order, if you look at the columns of your Koleski decomposition, really those are basis elements. So it's saying I can represent the Gaussian process by taking each one of these basis elements, hitting them with a standard normal, and then adding them all together. That's how I get a realization from a Gaussian process. There's just one way of thinking about it. And it's just that this basis isn't great for computational reasons. So if you do something like Koleski with pivoting, you'll get a different set of bases. But what you'll notice is that you have a much fewer ones that are substantial than lots of them that are near 0. So that means really, if you thought about a Gaussian process realization, it has about 6 or 7 degrees of freedom the way I showed it. And then most of these bases don't really matter. So there's bases, there's Koleski with pivoting. I think that's what we have in our lab. And then if you did SVD, you get a slightly different basis set. But the point is that the way you build multivariate normal realizations is you build bases, say with a Koleski or some sort of matrix decomposition, and then you hit those bases, multiply them by a standard normal, and then add it all together. So that's how you get your functions. And lots of things work that way.
The basis is your K.
So the way I have it here is the basis is the I try to switch every I try to switch each time, but yeah, it's L here. It was K just before. Yeah. Yeah. So it's the columns of that matrix. All right, and often you don't need every single column. You can stop after a few of them. And you might have enough variation that is really, it's just extra effort to carry the rest along. And so when people do rank deficient Cholesky sorts of things like that, this is what they're doing. OK, so now what we can do, and we'll do this in the lab if we get there, we can generate realizations of the multivariate normal. And here's just a sample, so I think we have exactly this plot you get to make in the lab. So here are just some realizations. I put the dots in there to remind us we're really doing this with a vector of maybe 40 dots in here, so we just have 40 locations across the spatial dimension. And we're just generating them according to a multivariate normal formula. So here are realizations of this thing. And so why you might like this as a prior model for a function is that the function can do lots of different things. The correlation matrix, though, tells you how smooth it is, that all these things have about the same smoothness attached to them. So if you make the correlation die out more quickly, so correlation dies more quickly as a function of distance, you'll get more wiggly sorts of realizations. If you have the correlation die out more slowly, you'll get less wiggly things. We like less wiggly things for emulators. It's going to make our life better. All right, so those are realizations from that multivariate normal density. And those are the building blocks for Gaussian processes. All right, so here is the big secret to Gaussian processes is about conditional distributions. So what's going to happen is you have an unknown function, unknown realization of the Gaussian process. And what you're going to see are just parts of it. So now we have this unknown realization, this blue line, and what we see are just 2 dots. And what we'd like to do is fill in where is the rest of it. And we don't want to just fill it in. We want to say something about the uncertainty about where the rest of it is, or what might plausible realizations of that function be. So this is sort of the main thing that we always do in Gaussian processes. So let's go back to our 8 vector now. Let's make this thing the 8 vector and one on each number here. What we can do now is just sort of reorder it. So we put the 2 values we're going to condition on. So the value at s equals 1 and the value at s equals 4, we're going to put those up front. And so because I have s1, s2, s3, I didn't number them quite right. Here's the 2. We're going to put those up front, and we're going to put the rest kind of in order going across down below us. So I've just reordered this matrix a little bit, right? So here's my normal 0, sigma. I've just reordered things. So now what I want to do is I want to condition on these 2 guys and ask, what's the distribution of the rest of this stuff? And this is just a conditional normal formula that I'm hoping is on the next slide. Whew. All right, so there it is. So if I break up a normal vector into 2 components, z1 and z2, it's multivariate normal. So there's the covariance matrix. The distribution of z2 given z1, meaning the whole rest of the blue line, given those 2 points that I see, follows a normal distribution. It's just modified a little bit. So it has a modified mean now. So now it has a non-zero mean because it depends on what those 2 dots are. And then it also has a covariance that was the old covariance sort of knocked down some. So if you do Kalman filters and things like that, Kalman gain, this is just telling you how much you've gained on how much you've reduced your variance now by these observations. So this is familiar stuff depending on your language. So now we have this new multivariate normal distribution. It has a mean and it has a covariance. I can do draws of this thing, and that's all I've done here. I've just done draws on that multivariate normal distribution. And because I've conditioned on those 2 points, all these draws have to go right through those 2 points. And if you look at the covariance that you made here, what's going to happen is the covariance is going to come down to 0 when I get close to those points, and then it's going to go back up again as I leave them. So here are plausible realizations for this Gaussian process once I know those 2 points. All right, so what's nice about that is you have a nice probabilistic description for this unknown function that you're trying to estimate. And so this is nice to throw it into some larger formulation because now this is something you can work with. All right. All right, and what often happens is we don't have these points exactly, right? We kind of estimate these points with observation error. So the last thing I want to just mention for calculations here is what happens if you have observations that are uncertain. So here's our setup that what we observe, these black dots, are we're going to model them as a Gaussian process plus extra noise. And this extra noise we're going to assume is IID normal 0 sigma squared. So that means it's going to vary about, it's not going to be right on the line, but it's going to be somewhere close. So if you look at these black dots, they're somewhere close. And here's 2 SDs, so I'm saying the SD of these things is probably around, I don't know, 0.2 or something, or 0.5. So that tells you how much variance I have in this noise piece here. All right, so I've got data that's centered at the Gaussian process, but has a covariance that's just sigma squared times the identity matrix. And I've got a spatial process prior, or a Gaussian process prior, that's mean 0, but special covariance matrix for the underlying blue line. So those are the 2 things that we got there, right? You might also say it this way. We've got the likelihood over there on the left. We've got the prior over here on the right. OK, so now if we go ahead and do inference here, we can either think of it as the likelihood times the prior, or even more easily, we can think of just using that conditional formula. All right, and also I've written the likelihood and the prior there. All right, so we can think of it as prior or likelihood, but I'm not going to subject you to that. I don't think. But I could. But here's what I'll subject you to is to get this answer, all we have to do is just the conditional formula. So here's how you can use just the conditional formula. You can say I've got y, vector of say 8 y's and a vector of 8 z's, or z stars here. That's what I've got. And the whole thing jointly is going to be normal, mean 0 to start. I have error covariance for the y's, and then I have spatial covariance for the y and z together. So if I thought about that thing, the y's have this spatial covariance plus this error part. So it's the convolution, right, of the errors and the Gaussian process. And that makes sense here because I am adding the 2 variance components to that. And then the z part, the underlying smooth function, has just the spatial covariance part attached to it. All right, so if I do it that way, then I can just use that conditional formula. So I can build a big covariance matrix for sigma z here, and I can just use that conditional normal formula to figure out what's the mean of the underlying smooth thing given the data y. And so I use the conditional normal formula, I'll get a mean and I'll get a covariance for that smooth process that's underlying there. And then I can just generate realizations from this thing. And that's what I'm showing here. So here's also a way you can get realizations of that underlying function as a function of noisy data. And again, it's just using that conditional normal formula. So all right, we'll do one example. And maybe we'll see if there's any questions left, or maybe I'll show you how you might use it in more serious settings. But also in the lab for the advanced class, here are some concentration measurements at a contaminated site with dioxin. So over here are just places where they've sampled the soil and have measured the dioxin concentration. So the spatial extent is 0 to 100 meters, 0 to 200 meters in the y direction. What you might like to do is build a map of the spatial concentration of dioxin across here. So we've got these points that we want to fill in. They're probably noisy, so we'd use the formulas on that last page here. We'd have to estimate and decide what the covariance function is. But basically, just using that, picking a covariance function, we can come up and fill in the concentration, or we can generate realizations of the ozone dioxin concentration given the measurements here across this spatial area. So there, if you thought about it, the y's that we got is these 200 measurements here. So we have 200 measurements. Those would be the y's. For the z that we want to reconstruct, it lives on this regular lattice that's, I can't remember, like 40 by 20 or something like, or 20 by 40, something like that. So I have a regular lattice where I'm trying to make the prediction z. I've got data. It's about 200 points. And I can throw it back into that formula there. All right, exactly what parameter settings I want. And that's a little more advanced. So you might try out a few and see what makes sense. So you can try different covariances that depend on distance. And you might have it die off quickly with distance, die off slowly with distance, and see what seems to give a good number there. Or you can more formally do that and ask what correlation distance gives me the highest likelihood, or fold it into the Bayesian inference. And then at the end, I can look at the posterior standard deviation. So I have this big, giant covariance matrix. I can look at the diagonals and take the square root, and that's just a map of that. All right, that is Gaussian processes. There's an actual real attempt you can try on that thing. And what do we use Gaussian processes for? Often we're trying to fill in what a computer model, a big computational model might say at places we couldn't afford to run it. So, so in those cases, we might have a lot more dimensions than 1 or 2. So we got to worry about that a little bit more. Often, though, computer model output is smoother. So usually we don't have a big noise issue. So that typically there's maybe a little bit of numerical noise that happens when you change your input settings. But there's not that much in terms of, you tend to not have much noise, so it really does want to interpolate. So I'm tempted to stop here, but just say that yeah, there's a lot of other things you can do to try to estimate stuff. And so the notes are all online on our website here. Here's attempts to actually estimate more things, say with Markov Chain, Monte Carlo, and Gaussian processes. Here we're actually estimating the width of the covariance function, how fast does the covariance die off. We might also try to fill in a computer model. So here's an example of a set of runs from computer models, 6-dimensional inputs. And now we want to figure out what would the computer model say in other places. We also want to know what inputs are really sensitive to the outputs that we're looking at. And so fitting a response surface to something like that would be important. Often we build the correlation function, the distance, to depend on dimension. So for input 1, we'll estimate a correlation distance. For input 2, we'll estimate a different correlation distance, and so on, and get some sort of response surface to that. But that's an advanced course. We're just doing the starter course here. So I will end it there, and you're welcome to ask me questions or yak with me afterwards.
Questions?
Yeah, so you mentioned the role of the kernel. So
Yeah.
to be a Gaussian process, you do not need to pick the kernel, which itself is Gaussian.
Yeah, so yeah.
You can pick something else as well.
A coincidence in that case, yes. So the kernel or the covariance function I picked to be Gaussian, that will give you very smooth realizations, in fact, infinitely differentiable. Another popular choice, especially for environmental processes, to have that die off exponentially. So e to the minus distance.
Right.
And those tend to give you much rougher looking processes, nowhere differentiable, but still continuous.
So once you have picked your kernel, then there is a way to systematically pick the parameters for that particular kernel, right?
Yeah.
I mean, that framework you can build.
Yeah.
But is there a systematic way of picking the kernel as well, the shape of the kernel?
So you could embed the kernel choice. Like Matern class has a local smoothness parameter in it, where you go from something that's very rough to something that's more and more differentiable. So you could also fold that into your inference as well. It turns out if you have noisy observations that aren't real tight, it's hard to get a lot of information on that. So, so depending on how your measurements are, you may not be able to get very tight inference on the nature of that process. Is it smooth or is it wiggly? But environmental things, concentrations of various sorts of things tend to be pretty wiggly. And those you tend to have a covariance that dies off more quickly initially. Things like output from computational models tends to be very smooth. In fact, the actual mathematical model it's representing might be provably analytic. And so there you might want something a lot smoother. So a Gaussian kernel is very common there for that reason.
Just to pick up that last point you made about the output of models being smoother, and you implied that the non-smoothness would be down to numerical artifacts. But I mean, I'm thinking of the atmospheric application. Wouldn't the internal variability in sampling be much larger?
Atmospheres, yeah.
So
yeah.
Then you wouldn't have a smooth field anymore. You'd have to have some kind of estimate for your output length.
Yes.
Wouldn't that actually kind of massively dominate the numerical non-smoothness, so to speak?
Yeah, we've tried atmospheres, and those have a lot more noise, especially if you can average over a long time, then maybe they'll start looking smooth as you change parameter settings in the model. But yes, you're right about that. And this
what
makes it a
about
lot harder.
if the output that you're looking at is non-Gaussian in nature? So if you're looking at precipitation, do you have to make a trick to try and transform it into a Gaussian or a variable that has Gaussian errors? Or
Yeah, good question. So let me get to a picture somewhere here. Yeah, so what's Gaussian is really any one point by itself needs to marginally be Gaussian, so that if you looked at the function you've got, and then I sort of marginalize it sideways, it doesn't have to look very Gaussian at all in that case.
Right, okay.
So it tends not to be all that restrictive, even if you're looking at something like precipitation. What it's not good at, though, these sorts of Gaussian processes, if you have something that stays 0, 0, 0 for a long time, then suddenly sort of ramps up.
Right.
It tends to have artifacts where it wants to go down before it ramps up a little bit, so it'll get this sort of weird kind of bending in it, because it's not a good model for things like that.
And presumably you can always average over a longer period of time to make things look more Gaussian anyway.
Yeah.
With rainfall once you
Yeah.
do monthly or annual means.
Yeah, so that's right. And where in climate where these have been useful, has been much more, all right, let's take decadal averages or something like
Right.
that and ask.
The problem goes away.
Yeah.
Thank you.
So why didn't it work when we tried the Gaussian process for emulating the 8x8 set of experiments? What was the issue?
Yeah, so so we tried this out for a 2-parameter variation set that was a whole field of atmospheres. Is that right? Or a number of different outputs,
I think
right?
we were trying to emulate temperature and precipitation.
Yeah.
I think,
So we were trying to get these whole spatial fields, but it wasn't and then we tried to average over longer and longer time periods.
yeah.
And at the very long time periods, you could kind of reconstruct it, but you couldn't get all the features. Clearly, the models had more features than the Gaussian process was absorbing. And why was that?
I remember looking
Yeah.
at the emulated output, and it would produce unphysical structures
Yeah.
and predictions, like structures across the tropics that were not,
Yeah.
I was unhappy with.
Yeah, no one was terribly happy. But so what we were trying to do was not emulate a single point as a function of the input parameters, right? So a single function, but now a whole spatial field. And it would have all right. So it does well with kind of this up and down sorts of things, but if features sort of shifted across space, even if it did it smoothly, well, it's not a natural setting now for the Gaussian process. That it can you'll have to go down here and up here, or a wave will have to kind of follow and move across in order to match that. And that's not, it's good at matching things, functions that change height as a function of the parameter settings, but if features move spatially, it's not that good for something like that. And it's because sort of shifts across space aren't really linear transformations of what you had before. They're
Did you use the 8x8 where you're having a single member for each parameter setting? Because if you actually had an ensemble for each parameter setting, you might be able to actually have a...
We had an ensemble.
You had an ensemble for each parameter setting. So it was 8x8 by an ensemble direction of initial condition perturbation.
That's right.
Okay, so it was actually much higher.
Yeah. So it was definitely a much tougher task. That where Gaussian processes been good for very aggregate sorts of measures. Global temperature, I think, kind of was okay, or if you also spatially averaged or something somewhere, it could get things like that. But the actual details of the spatial field, still, it wasn't that great with that. In other settings, if we look at some physics experiment, if we look at some very integrated measure, the time it took to crush down to some shape, something very aggregated like that did well with the Gaussian process. Things like timing were not quite as good. When did the peak feature show up? If you're trying to reconstruct the whole trace of the compression curve or something like that, because the compression curve would shift again, the Gaussian process did not do as well. But if you just grabbed the one feature and asked, okay, now I'm just modeling where is it as a function of space, it could do something like that because it was trying to reconstruct this whole feature as a function of space. So there are definitely places where it did not do so well. And places where it did well, it was a pretty dang simple function of the input parameters that quite often would look not quite planar, a little bit curved and things like that, but it wasn't like going up and down and back up or something like that. So it tended to be like where you do well, in hindsight you say, oh, it's a simple problem. You finally figured out all you did was figure out how it was simple. And things that tend to be trickier, I don't know. open question, I think.
I think we should break for lunch.
Oh, yeah.
Just a reminder that we're going to have this little, oh yeah.
In 15 minutes, we got the R session.
Excellent. So T minus 15 right now.
All right.